Am I perfectly audible, visible to everyone? Just let me know once in the chats quick. Just let me know in the chats quick, people. If all of you can hear me, if I'm perfectly audible, visible to every one of you. I think yes, huh? All right. So how are you all? How are you all doing? All well? All good? I'm meeting you after so long on YouTube. Yeah. How are you all doing? All well? All good? Tell me once in the chats. Tell me once in the chats. Good evening, people. Good evening. Good evening and welcome back. Good evening and welcome back. Good evening and welcome back. So as you all must be knowing, today we are starting the General Organic Chemistry, right? The GOC, one of the most scoring chapters of your chemistry, right? The chapter that forms the foundation of your entire organic chemistry that we are going to start from today. And there were a lot of students asking me whether I'll be starting this chapter from the basics. Absolutely, I'll be starting this particular chapter from scratch, from zero, and I'll slowly level up things in this particular chapter. Okay? And my dear students, at the same time, well, I'm not going to cover this particular chapter in one go. I'm not going to cover this particular chapter in one session. What I'll be doing is, I'll be covering this particular chapter in 2 to 3 parts. And the duration of every part will be almost 3 hours. Okay? That is going to be convenient for everyone, I believe. Yeah? All right. I hope you understood what I said. This particular chapter I'll be covering in depth, in detail, exactly in 2 to 3 parts. Yeah? And once we are done with the GOC, then we are going to do isomerism, right? Similarly, chemical bonding and all the other chapters which we have not covered yet on YouTube on this particular channel. Perfect. So should we start then? Should we start, people? All ready? All ready? Let me know in the chats quick if everyone is ready. Yeah, I would want some fire emojis in the chats so that I'll get to know whether all of you are super duper excited about this particular session or not. Let me know quickly in the chats. Let me know quickly in the chats, everyone. Well, again, I'm repeating, this particular chapter I'll be covering in 2 to 3 sessions. And this is going to be the first session. And from now onwards, you are going to see me regular on this particular Unacademy NEET English channel. Yeah? Someone is saying, sir, I don't know chemical bonding. It's okay. Don't worry. You just watch this particular session. Wherever the concepts of bondings are required in this particular chapter, I'll be covering them here only. Yeah? Okay, so again, this particular chapter I'll be covering in 2 to maximum 3 sessions. Today is the session number 1. And on Wednesday, it's going to be session number 2. Okay, on Wednesday, it's going to be session number 2. Either I'll be covering in 2 sessions or maximum in 3 sessions. Duration of today's session will be almost like 3 hours. All right? Perfect. My dear students, whatever things I'll be writing on the screen, I would want every one of you to take a note of every single thing, right? Because I always believe that handwritten notes are better than the session PDFs and all which you keep on getting. So be ready with your pen and paper, right? And keep on writing all the things which I'll be writing on the screen. I hope that's clear to everyone. So without wasting a lot of the time, let's get going. Let's get started. And my dear students, it is the high time to start your organic chemistry from the chapter that is General Organic Chemistry, my dear students. General Organic Chemistry. So first of all, in the General Organic Chemistry, what all topics do we have? In the General Organic Chemistry, in the GOC, what all topics do we have? First of all, we shall be discussing about the basics of organic chemistry. Complete basics I'll be talking about in the beginning of this particular session. Then it's going to be the second topic is going to be inductive effect. Similarly, there will be resonance effect, mesomeric effect, aromaticity, and hyperconjugation. These are going to be the topics, right, which come in this General Organic Chemistry, my dear students, right? There are some other topics, other small topics as well, which I have not mentioned here on the screen, like your SIR, right? Questions based on bond links, etc., etc. There are many things which I'll be discussing in detail. So why I thought to complete this particular chapter in 2 to 3 sessions? Because I would want you guys, I would want to teach this particular topic in detail, in very much depth, right? That's why I have thought to schedule like 2 to 3 sessions for this particular chapter. Okay? Perfect, guys. So let's get going. Let's get started with some basic things, basic terminologies, which we are going to frequently use in the entire organic chemistry. Let's try to cover those basic terminologies first. And my dear students, I shall be starting with a term. I shall be starting with a term. What is that? That is the charged species and their stability. I shall be starting my lecture with a term called as charged species and their stability. Charged species and their stability. First of all, how do we exactly define a charged species? What is a charged species? You must be thinking, what is a charged species? My dear students, in simple terminologies, I can say any atom or a group of atoms, any atom or a group of atoms having any type of charge on it, which can be either positive or negative. Whenever you will see an atom or a group of atoms having any sort of charge on it, be it positive or negative, you call that particular species, you call that atom or group of atoms having any sort of charge on it, you'll be calling that as the charged species, right? My dear students, for the charged species, what do we define? For the charged species, we define a term called as volume charge density. For charged species, we define a term that is called as volume charge density, and volume charge density is represented with VCD. And what is this volume charge density? First of all, it is a term that is defined for charged species. And what this volume charge density is all about? It is nothing but, it is the ratio of charge on the species. It is the ratio of charge on the species to that of the size of the species. It is the ratio of the charge on the species to that of size of the species. Now, first of all, what kind of information this VCD, this volume charge density, gives me? Before talking about that, let's try to understand this VCD a bit more in detail. Have a look, guys. I told you volume charge density is nothing but it is the ratio of charge on the species to that of size of the species. So, for example, just to make you understand, let's say this is an atom carrying a charge. Okay, this is one more bigger sized atom carrying a charge. Let's say the charge on both the species, let's say the magnitude of charge on both the species is same. Let's say the magnitude of charge on both the species is same. But if I ask you, is the size of both the species same? No. Size of this particular species is more. And more the size of the species, lesser will be the volume charge density. As simple as that. Okay. For example, this is an atom carrying a negative charge. This is one more atom carrying the negative charge. Perfect. Let's assume the magnitude of charge on both the atoms is same. Let's assume magnitude of charge on both the atoms is same, right? But is the size same? No, size is different. I would say this particular species has got more size, and more the size of the species, lesser is going to be the volume charge density. Okay, lesser is going to be the volume charge density. So volume charge density which we define for the charged species is nothing but it is a ratio of charge on the species to that of size of the species. Now let's try to link this term volume charge density with the stability. My dear students, remember one simple term from now onwards which I'll be using in the entire chapter basically. What is that? Remember, as the volume charge density of a species increases, let me tell you, potential energy of the species increases. And as the potential energy of the species increases, as the potential energy of the system increases, I would say, what happens to stability? Since all of you would be familiar with the fact, more the potential energy, lesser is going to be the stability. So if I would want to relate volume charge density with the stability, how do I relate it? I would say stability of a species, stability of a charged species, that is inversely proportional to what? That is inversely proportional to volume charge density. This is one important parameter which I would want every one of you to remember from now onwards. Okay? So first of all, whenever you see an atom or group of atoms having any sort of charge on them, you call those atoms or group of atoms which have got certain charge on them, you call them as the charged species. And for the charged species, what do we define exactly? We define a term called as volume charge density, which is nothing but the ratio of charge to that of size. And more the charge on the species, more is going to be the VCD. Lesser the size of the species, more is going to be the VCD. And as the volume charge density increases, potential energy of the system increases, and as the potential energy increases, I would say stability automatically decreases. So remember from now onwards, stability is inversely proportional to what? Stability is inversely proportional to VCD, and VCD stands for volume charge density. I believe this particular stuff is clear to every one of you, right? Now, my dear students, there's a term which I'll be frequently using. What is that? The term is your electronegativity. I believe all of you would be familiar with this term already, but still, let me talk about this particular term a bit more here, because frequently in this particular chapter, I'll be using this term. How do we define the term electronegativity? My dear students, electronegativity is nothing but it is the tendency of an element to attract the bonded pair of electrons, towards itself. What does that mean? For example, imagine that there is a single covalent bond between A and B. Imagine that there is a single covalent bond between A and B. And you know, a single bond consists of two electrons. These are the two electrons, right? Let's say there's a covalent bond. So I would say the electron pair which forms the bond, let that electron pair be at the center right now. Because this electron pair, it will be mutually shared by A as well as B, since I'm talking about the covalent bond, right? This electron pair, it will be mutually shared by A as well as B. Now, for example, if I say electronegativity of B is more than that of A, my dear students, think about it. If electronegativity of B is more than that of A, that means B has got more tendency to attract this bonded pair towards itself. What will happen due to that? I would say this electron pair will be slightly shifted towards B, right? The electron pair which was supposed to be at the middle, since B is more electronegative, so it has got more tendency to attract the electron pair towards itself, due to which the electron density towards B increases, and that increase in the electron density is represented by delta negative. That decrease in the electron density towards A, I'll be representing that with delta positive. As simple as that, right? As simple as that. My dear students, for example, there is a double bond between A and B. Double bond means there will be two electron pairs here. There will be two electron pairs. Now, I'm assuming that electronegativity of B is greater than that of A. So what will happen due to that? I'll say B has got more tendency to attract both the electron pairs towards itself, due to which these two electron pairs will be towards B. These two electron pairs will be towards B, right? So I would say, my dear students, the electron density towards B has increased, and that increase in the electron density I'll be representing with -2 delta, and here I'll be writing +2 delta, because towards A, electron density has decreased. And similarly, if there is a triple bond, between A and B, so I would say all the 3 electron pairs will be towards B, so B will get -3 delta, A will be getting +3 delta, correct? At the same time, my dear students, remember one more thing. In your periodic table, fluorine is considered to be the most electronegative element, followed by oxygen, followed by nitrogen. In your periodic table, fluorine is considered to be the most electronegative element, followed by oxygen, followed by nitrogen. One more thing which I would want you guys to remember. What is that? Remember one simple thing. What is that? My dear students, electronegativity. Electronegativity. That is basically inversely proportional to size. Electronegativity, that is inversely proportional to the size of the atom. So, if I do one thing, if I move from left to right in the periodic table, what happens to the size generally? If I move from left to right in the periodic table, I would say generally the size decreases. And if the size decreases, that means electronegativity should automatically increase. Electronegativity should automatically increase when you move from left to right. Similarly, my dear students, when you move from top to the bottom in the periodic table, what happens to size? Size generally increases. And as the size increases, I would say electronegativity will decrease when you move from top to the bottom. Perfect. Now, what kind of other information can we get from the term electronegativity? What kind of other things should come to our mind when you hear the word electronegativity? Let's talk about those things as well. My dear students, for example, look at this particular slide, one of the important slides. Okay, have a look. I've mentioned a statement over here. My dear students, electronegativity, it gives us the tendency of an atom. It gives us the tendency of an element to hold its valence electrons. Electronegativity of an element, it gives me an idea about how much capable an atom is to hold its valence electrons. Do you understand that? If I talk about, my dear students, if I talk about electronegativity of an atom, it gives me an idea about the tendency, about the capability of the atom to hold its valence electrons, right? Since you know, in an atom, nucleus will be always holding the valence electrons, right? Now remember, more the electronegativity of an atom, more the electronegativity of an element, more is the tendency to attract the valence electrons towards itself, right? So I would say more electronegative element has got more tendency to hold its valence electrons. More electronegative element has got more tendency to hold its valence electrons. For example, if you talk about fluorine, right? If you talk about carbon, perfect. I've selected 2 elements here, right? My dear students, since fluorine is more electronegative than carbon, if fluorine is more electronegative than carbon, that means fluorine has got more tendency to hold its valence electrons. Okay, so more electronegative element has got more tendency to hold its valence electrons. Number 1. Number 2, this electronegativity gives us an idea about, it gives us the idea about the negative charge holding capacity of an element. It gives us an idea about the negative charge holding capacity of an element. My dear students, remember one thing. More the electronegativity of an element, more will be the tendency of an element to hold the negative charge, to sustain the negative charge. What I'm trying to say is, more the electronegativity of an element, more will be the tendency of an element to hold the negative charge on it, to sustain negative charge on it. So, for example, if I talk about oxygen carrying negative charge, if I talk about carbon carrying negative charge, right? Now, my dear students, since oxygen is more electronegative than that of carbon, If oxygen is more electronegative than that of carbon, that means oxygen has got more tendency to hold the negative charge. And more the tendency of an element to hold the negative charge, I would say more will be the stability of negative charge on oxygen. I would say this negative charge will be more stable on oxygen than that of carbon. So remember, electronegativity of an element, it gives me the idea about the negative charge holding capacity of an element as well. And more the electronegativity of an element, more is the tendency of an element to hold the negative charge, to sustain the negative charge, right? So more will be the stability as well. And my dear students, remember one thing I'm going to tell you. Remember the negative charge carrying capacity. The negative charge carrying capacity. The negative charge carrying capacity of one oxygen atom. The negative charge carrying capacity of one oxygen atom is greater than the negative charge carrying capacity of almost 10 carbon atoms. Now you can understand how stable negative charge will be on oxygen as compared to carbon. Do you understand what I'm trying to say? The negative charge holding capacity of oxygen is more than that of negative charge carrying capacity of almost 10 carbon atoms. Now you can understand how stable negative charge will be on oxygen as compared to carbon. Yeah? Right? So first of all, electronegativity. It gives me the tendency of the element to attract the bonded pair of electron towards itself. Number one. It gives me the idea about the tendency of an element to hold its valence electrons. Right? Number three. It gives me an idea about the negative charge holding capacity of an element. As simple as that. More electronegative element can hold negative charge more. Right? Now, this particular statement I would want you guys to remember as well. Electronegativity of orbitals is also defined, and s orbitals which are closer to the nucleus. S orbitals, this is p for example, just to make you understand, this is d, this is f, right? S orbitals have got more electronegativity than that of p, than that of d, than that of f. What does that mean? That means if the electron is present in s, since s is closer to the nucleus, so it will experience more attraction as compared to the electron which will be present in p, as compared to the electron which will be present in d. Right? Perfect. I believe I'm clear till here. I believe I am clear till here. Now, my dear students, something which is very important and you should know that too. If I talk about carbon, if I talk about the element carbon, my dear students, carbon shows what kind of hybridization? Carbon shows sp-I hybridization. sp-I hybridization. And this I can be 1, it can be 2, it can be 3. So technically I would say, if I talk about carbon, carbon is going to show 3 types of hybridizations basically. Carbon is going to show 3 types of hybridizations. One is called as sp, one is called as sp2, and one is called as sp3. Carbon can show sp hybridization, carbon can show sp2 hybridization, carbon can show sp3 hybridization. So what this sp hybridization is all about, what this sp2 is all about, what this sp3 is all about. So for that you should know first of all what hybridization is all about. What is hybridization? In hybridization, what happens? In hybridization, the atomic orbitals of a bonding atom, they are going to intermix. And they lead to the formation of new orbitals called as hybrid orbitals. For example, let me make it clear to you. If I talk about carbon, carbon's outermost configuration is 2s2, 2p2, right? 2s2, 2p2. This is your s orbital here. These are the 3 p orbitals of carbon. Perfect. Now, this is s for example. This is your px, this is py, this is pz for example, right? So, what is going to happen in sp hybridization? In sp hybridization, I would say s orbital of carbon and the p orbital and one of the p orbital of carbon, they are going to intermix and they will lead to the formation of what? They will lead to the formation of hybrid orbitals. And remember, number of atomic orbitals mixed will be equal to the number of hybrid orbitals formed. So this is one hybrid orbital, this is one hybrid orbital. Now, these two hybrid orbitals, they'll arrange themselves in such a way that there should be minimum repulsions between them. So these are the two hybrid orbitals basically. Each hybrid orbital here I'll be calling as sp hybrid orbital. So this is sp hybrid orbital. This is also sp hybrid orbital. Now, how this sp hybrid orbital has got formed? This sp hybrid orbital has got formed when the atomic orbitals, when these two atomic orbitals have intermixed basically. So I would say the sp hybrid orbital will definitely have some percentage of s character as well, right? This sp hybrid orbital, since it got formed due to the intermixing of s and p, so I would say each sp hybrid orbital will have some percentage of s character too. Now, if I ask you what is the percentage of s character in sp hybrid orbital, you will say, since there is one s orbital used, divided by, in total there are two orbitals used, multiplied by 100. So percentage of s character in sp hybrid orbital is nothing but 50%. Now, if you look at this particular in sp hybridization, what is the bond angle? If I talk about the bond angle will be simply 180 degree. Bond angle will be 180 degree. So percentage s character 50%, and in sp hybridization, what is the bond angle? Bond angle is 180 degree. Correct? Now, talk about sp2. In sp2, what happens? S orbital and these two p orbitals, they are going to intermix, right? And when they intermix, since three atomic orbitals are intermixing now, so three hybrid orbitals will get formed. So these are the three hybrid orbitals. And these three hybrid orbitals, my dear students, they are going to arrange themselves in such a way that there should be minimum repulsions between them. Right? So they are going to arrange themselves at an angle of what? They are going to arrange themselves at an angle of 120 degree. Perfect? They are going to arrange themselves at an angle of what? 120 degree. Now, each hybrid orbital here will be called as sp2 hybrid orbital. Now, if I ask you what is the percentage of s character? What is the percentage of s character in sp2 hybrid orbital? You will say there is one s orbital used, divided by, in total 3 orbitals were used, multiplied by 100. The value comes out to be 33%. So this is the percentage of s character in case of sp2 hybrid orbital. And same goes for sp3. If I talk about sp3, in sp3, there'll be 4 hybrid orbitals formed, and they'll be placed at an angle of what? They'll be placed at an angle of 109 degree 28 minutes. They'll be placed at an angle of 109 degree 28 minutes. And my dear students, at the same time, if I ask you, in each sp3 hybrid orbital, what is the percentage of s character? I would say percentage of s character will be equal. How many s orbitals are used? 1. How many total orbitals are used? 4. Multiplied by what? Multiplied by 100. The value comes out to be 25%. Right? Perfect. Now, what can you conclude from here? What can you conclude from here? As we move from left to right, what is happening to s character? When we move from left to right, the s character is decreasing. S character is decreasing. At the same time, when we move from left to right, what is happening to bond angle? Bond angle is also decreasing. Bond angle is also decreasing. So can I generate a relation between s character and bond angle? Absolutely, I can generate a relation. The relation is going to be pretty simple. What is that? I would say, my dear students, I would say bond angle is directly proportional to percentage of s character. Bond angle is directly proportional to percentage of s character. And few minutes back I told you, more the s character, more is going to be the electronegativity. More is going to be the electronegativity. Remember this particular point as well. So my dear students, if I ask you, among sp hybrid orbital, among sp2 hybrid orbital, and among sp3 hybrid orbital, which one do you think will have more electronegativity? Wherever s character is more, electronegativity is going to be more. Right? Electronegativity is going to be more. So I would say electronegativity of hybrid orbitals is also defined. Remember, more the s character, more is going to be the bond angle, more is going to be the electronegativity. So this is the electronegativity order which I wanted to convey here. Perfect. So remember this particular point. Your electronegativity, that is directly proportional to what? That is directly proportional to the percentage of s character. I believe this is clear. If yes, let me know once in the chats quick. Quickly, people, in the chats. Yeah? Now, my dear students, this particular point is clear. Now, talk about this particular point. Look at this particular molecule. Let me make this molecule separately here somewhere. This is carbon. attached with a hydrogen, carbon, triple bond carbon. This is CH. This is CH, and this is double bond, and this is CH2. This is CH2. Now, my dear students, do just one thing. Tell me how many sigma bonds this carbon is making. I would say this carbon is making 2 sigma bonds. 2 sigma bonds means this carbon is showing sp hybridization. Okay, right? Now, similarly, if I ask you what is the hybridization of this particular carbon, how many sigma bonds it's forming? 1, 2. 2 sigma bonds means sp hybridization. If I talk about this particular carbon, how many sigma bonds it's forming? 1, 2, and 3. 3 sigma bonds. 3 sigma bonds means this carbon is showing sp2 hybridization. And even this is forming 3 sigma bonds, so this is forming sp2 hybridization. This is showing sp2 hybridization, right? Now, my dear students, if you select this particular carbon, since this particular carbon is sp hybridized, and electronegativity of sp is more than that of sp2, so this carbon is more electronegative. If this carbon is more electronegative, it will attract the bonded pair towards itself. And when it attracts the bonded pair towards itself, so this carbon will be getting delta negative, and this carbon will be getting delta positive. So can I say, due to the difference in the hybridization, due to the difference in the electronegativities, can I say a molecule got partially polar? Partial polar character got developed in a molecule due to the difference in the hybridizations, due to the difference in the electronegativities. Say yes or no in the chats. So I would say the molecule, it can become partially polar because of the difference in the hybridization, right? Because of the difference in the electronegativities. Yeah? Am I clear with this, everyone? And if I'm clear with this, let's talk about a few more things. My dear students, there's a term called as angle strain. You should know that term too, because frequently you will come across that particular term in this particular chapter. First of all, look at this 3-membered ring. It is basically your cyclopropane, cyclobutane, cyclopentane, cyclohexane, right? If you talk about this particular carbon, carbon is forming 1 bond, second. So there'll be 2 hydrogens attached as well, because carbon has to form 4 bonds, correct? Talk about this particular carbon. It's forming 1, 2, so there'll be 2 hydrogens as well. So 4 bonds. Select this particular carbon. Even it will be having 2 hydrogen atoms, right? Talk about this particular carbon. Even it will be having 2 hydrogen atoms attached to it, right? Now guys, what's going to happen? Understand what's going to happen. If I ask you how many sigma bonds this carbon is making, this carbon is making 4 sigma bonds. So I would say this particular carbon here, it is sp3 hybridized. If this particular carbon is sp3, I would say this particular carbon is also sp3. Even this particular carbon is also sp3 hybridized. This particular carbon is also sp3 hybridized, because every carbon right here is forming 4 bonds. Okay. Now, if every carbon here is sp3 hybridized, in case of sp3 hybridization, what is going to be the expected bond angle? Expected bond angle here is going to be 109 degree 28 minutes. Here also it's going to be 109 degree 28 minutes. I would say here also it's going to be 109 degree 28 minutes. And here also it's going to be 109 degree 28 minutes. This is the expected bond angle everywhere. Right? This is the expected bond angle everywhere. Now, if I ask you, the expected bond angle here is 109 degree. What is the actual bond angle? What is the actual bond angle here? It is 60 degree. If I talk about the actual bond angle here is 60 degree. For example, here, what is the actual bond angle? Actual bond angle is 90 degree. Do you understand? The actual bond angle is 90 degree. The actual bond angle is 90 degree. My dear students, remember one simple thing. Whenever the expected bond angle and the actual bond angle, whenever the expected bond angle and the actual bond angle come out to be different, whenever the expected bond angle and the actual bond angle come out to be different, at that point of time, we say the molecule is under angular strain. So I would say this particular molecule is under angular strain. whenever the expected bond angle and the actual bond angle, they come out to be different, at that point of time, we say the molecule is under angular strain. So all these molecules here, they are under angular strain. They are under angular strain. And remember, my dear students, more the difference between expected and actual, more the difference between expected and actual, more is going to be the angular strain. More is going to be the angular strain. More the difference between expected bond angle and actual bond angle, more is going to be the angular strain. And more the angular strain means, remember, more the angular strain means more the electronegativity. This is the point which I would want every one of you to remember. More the angular strain means more electronegativity, right? We can talk in terms of this. We can talk about this particular statement in terms of bond angle, the exocyclic bond angles. I'm not going there. That's of no use to us. Remember just one point. More the angular strain in a molecule, more is going to be the electronegativity, right, of the atoms forming the ring. So I would say this particular carbon would be more electronegative than that of this one, then that of this one, then that of this one. Correct? Now, my dear students, here I've got a 3-membered ring, here I've got a 4-membered ring. Both are joined. Perfect. If I talk about this particular carbon and this particular carbon, yeah, this particular carbon will be under more angular strain. It is 3-membered. It is 3-membered, more angular strain. More angular strain means more electronegativity. So this carbon is more electronegative than that of this one. If the electronegativity of this carbon is more, that means this carbon has got more tendency to attract the shared pair towards itself, due to which it gets delta negative and this gets delta positive. So again, I would say, molecule became partially polar. Again, I would say molecule became partially polar because of the difference in the electronegativities. And the difference in the electronegativities has arisen due to what? The difference in the electronegativities has arisen due to the angular strains in these rings. Yeah? Am I clear with this, people? Am I clear with this, everyone in the chats? Am I clear with this, everyone in the chats? Quickly. Quickly, everyone in the chats. Am I clear till here? Everyone means everyone. Right? I believe all the things which I discussed with you till now, I believe all the things are very much clear to you. Yeah? Amazing. Now, guys, there comes something important. What is that? Understand. I've mentioned the topic here as stability of charges. Stability of charges. What does that mean? For example, I'm telling you that oxygen is carrying negative here, carbon is carrying negative here, nitrogen is carrying negative here, fluorine is carrying negative here. And I want you to understand on which atom among these, on which atom negative charge will be more stable. I want you to understand on which atom negative charge will be more stable. So basically, I'm talking about the stability of the charges on the atoms. I'm talking about the stability of the charges on the atoms. Okay? Understand one thing, guys. Understand one thing. Whenever you have to compare the stability of the charges on the atoms which belong to same period. Whenever you have to talk about the stability of the charges on the atoms which belong to same period. For example, again, I'm giving the same example, carbon carrying negative, nitrogen carrying negative, oxygen carrying negative, fluorine carrying negative. I need to check on which atom negative charge is more stable. Whenever you have to compare the stability of the charges, on the atoms which belong to same period, remember, your answer will be, you'll give your answer as per electronegativity. You'll give your answer as per electronegativity. And my dear students, remember just one thing. Negative charge is more stable on more electronegative element. Because as I told you, more electronegative element has got more negative charge holding capacity. More electronegative element has got more negative charge holding capacity. So negative charge is more stable on more electronegative element. And remember, similarly, Positive charge is more electronegative, is more stable on less electronegative element. Negative charge is more stable on more electronegative element. Positive charge is more stable on less electronegative element. So whenever you have to compare the stability of the charges on the atoms which belong to same period, you'll give your answer as per electronegativity. For example, I have to talk about the stability of these charges. Chlorine carrying negative, oxygen carrying negative, nitrogen carrying negative, carbon carrying negative. Negative charge is more stable on more electronegative. So this is going to be the stability of the charges. This is going to be the stability of the charges, right? Yes. I believe this is clear to everyone. I believe this is clear to everyone. I told you one thing. Negative charge is more stable on more electronegative element, and positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative element. Now, can positive charge become more stable on more electronegative element anytime? Can positive charge become more stable on more electronegative element? Sometimes. That's the question. For that, remember this particular statement. Positive charge can become more stable on more electronegative element when its octet is complete. What does that mean? Look at this particular carbon, carrying positive, right? Look at this particular oxygen, again carrying positive, right? So technically, what should happen? Technically, I would say carbon and oxygen, they belong to same period. And in the period, if you have to talk about the stability of the charges, you talk in terms of electronegativity. And you know, positive charge is more stable on less electronegative element. Now, carbon is less electronegative than oxygen. So technically, positive charge on carbon should be more stable. Technically, positive charge on carbon should be more stable. But that's not the case. That's not the case. It is reverse here. Why is that? If I ask you about the octet of this particular carbon, see, 2, 4, 6. The octet is incomplete. Talk about the octet of this particular oxygen, 2, 4, 6, and 8. Octet of this particular oxygen is complete. So positive charge can become stable. Positive charge can be stable on more electronegative element when the octet is complete. When the octet is complete. Remember this particular point as well. This is again very, very, very important. Okay. Now, my dear students, as I told you already, whenever you have to compare the stability of the charges on the atoms which belong to same period, you will give your answer as per electronegativity. Negative charge will be more stable on more electronegative element. Positive charge will be more stable on less electronegative element. But whenever you have to compare the stability of the charges on the atoms which belong to same group, whenever you have to talk about the stability of the charges on the atoms which belong to same group, you won't give your answer as per electronegativity. You'll be giving your answer as per volume charge density. So remember, down the group, VCD dominates over electronegativity. Across the period, electronegativity dominates over VCD. Right? Yeah. Across the period, electronegativity dominates over VCD. Down the group. Remember, it's going to be VCD that dominates over electronegativity. And as I've told you already, VCD and stability, they are inversely proportional. VCD and stability, they are inversely proportional. For example, say, chlorine carrying negative, bromine carrying negative, iodine carrying negative. These elements, they belong to the same group. And I have to talk about the stability of these charges. on the atoms which belong to the same group. So I'll be talking in terms of VCD. My dear students, the charge on every atom is same. Now talk in terms of size. More the size, lesser the VCD. More the size, lesser the VCD. Lesser the VCD, more the stability. Right? I've told you already, your VCD, right? It's inversely proportional to size. And stability, that is inversely proportional to VCD. Correct? Since charge on every atom is same, so I'll be talking in terms of size. More the size, lesser the VCD, more the stability. So I would say negative charge will be more stable on iodine, followed by bromine, followed by chlorine, followed by fluorine. Yeah? I believe I'm clear. See, chlorine carrying positive, bromine carrying positive, iodine carrying positive. Now, again, all these atoms, they belong to same group. They belong to same group. Now, what do? These four atoms, they belong to same group. And in the group, VCD plays a role. Since charge on every atom is same, so talk in terms of size. So more the size, lesser the VCD. More the size, lesser the VCD. Lesser the VCD, more the stability. So positive charge will be more stable on iodine, followed by bromine, followed by chlorine, followed by fluorine. I believe all of this is clear. And if all of this is clear, then it's going to be the high time to solve the questions. Then it's going to be the high time to solve some basic questions, which can be framed from the terms, from the concepts that we have discussed till now. See, guys. Understand what I'll be saying. Understand what I'll be saying. Carbon carrying positive, nitrogen carrying positive, oxygen carrying positive, fluorine carrying positive. So they belong to same period. And in the period, we give our answer in terms of electronegativity. And we know positive charge is more stable on less electronegative element. Carbon is least electronegative. So positive charge will be more stable on carbon. Done? Done, people? Similarly, carbon carrying negative, nitrogen negative, oxygen negative, fluorine negative. Right? All these underlined elements, they again belong to same period. They again belong to same period, carbon, nitrogen, oxygen, fluorine. And in the period, we talk in terms of electronegativity, right? And you know, negative charge is more stable on more electronegative element. So fluorine is more electronegative. So negative charge will be more stable on fluorine. Yeah? Understood? Similarly, guys, talk about this particular question. Sulfur carrying negative, chlorine carrying negative. Now, sulfur and chlorine, again, they belong to same period. Again, they belong to same period, sulfur and chlorine. Sulfur has atomic number 16. Chlorine has got atomic number 17. So they belong to same period, right? If they belong to same period, talk about electronegativity again. So negative charge is more stable on more electronegative. Since chlorine is more electronegative than that of sulfur, so negative charge is more stable on chlorine than that of sulfur. Yeah? Now talk about this one. This is O, this is S, this is SC, this is T. This is O, this is S, this is SC, this is T. So all these elements, they belong to same group. These are group 16 elements. These are group 16 elements. So you have to compare the stability of the charges. You have to compare the stability of the charges on the atoms which belong to same group. So I'll be talking in terms of VCD, right? On moving from top to bottom, size increases. As the size increases, VCD decreases. As the VCD decreases, stability increases, right? So negative charge will be more stable here. This is the stability order. Am I clear till here, people? Everyone in the chats? Am I clear till here? Give me the answer of all these questions. Now you should be very quick in solving these questions. Nitrogen carrying negative, phosphorus negative, arsenic negative, antimony negative. All these elements, they belong to same group. And in the group, you talk in terms of VCD. On moving from top to the bottom, size increases. Size of this antimony will be maximum. More the size, lesser the VCD. Lesser the VCD, more the stability. So negative charge will be more stable here. This is the stability order. Oxygen carrying negative, sulfur carrying negative. Oxygen, sulfur, same group. VCD plays a role. Down the group, size increases. VCD decreases, stability increases. So this is the stability order. Yeah? Right? Talk about this one. Guys, have a look. This is your single bonded carbon. Yeah? Double bonded carbon. Triple bonded carbon. Where will be the S character more? S character will be more here. If S character is more here, that means electronegativity is more here. That means electronegativity is more here. And you know, positive charge is more stable on less electronegative element. So this is the stability order. Yeah? Similarly, talk about this one. Again, single bonded carbon, double bonded carbon, triple bonded carbon. Where will be the S character more? S character will be more here. Electronegative will be more here. And negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element. This is going to be the order. I believe all of this is super clear to everyone. If yes, let me know once in the chats quickly. Quickly, people, everyone. All clear till here? All clear? I believe yes. Okay, let's move on. My dear students, give me the answer of these questions. You can see all these are negative charges, right? This carbon carrying negative, this is the carbon carrying negative, carbon carrying negative, carbon is carrying negative. So where is the angle strain more? Where is the angle strain more? Angle strain is more here. More the angle strain, more the electronegativity. So this carbon is more electronegative, as discussed already. And you know, negative charge is more stable on more electronegative element, right? So this is going to be the stability order. Correct? Positive charge is more stable on less electronegative. This is less electronegative, so positive charge will be more stable here, right? Now, this is a special case, my dear students. This is a special case. This is the special case. Normally, if you see, this is your carbon carrying negative. This is your nitrogen carrying negative. Both belong to the same period. And in the period, we talk in terms of electronegativity. And we know, negative charge is more stable on more electronegative. Negative charge is more stable on more electronegative. So this should be the order. This should be the stability order. But, understand one thing. My dear students, this carbon here is sp hybridized carbon. This is your sp hybridized carbon. And this nitrogen here is sp3 hybridized nitrogen. This is your sp hybridized carbon. This is your sp3 hybridized nitrogen. Remember from now onwards, electronegativity of sp hybridized carbon is more than that of the electronegativity of sp3 hybridized nitrogen. So I would say here carbon is more electronegative than that of this nitrogen. Okay? And more electronegative means negative charge is more stable or more electronegative. So what is going to be the stability order? This is going to be the stability order. Am I clear with this? I believe yes. And if yes, let's talk about one more type of the question that can be solved based on the concepts that we have discussed till now. Okay? The concept is the acidic strength. Questions which are based on acidic strength. Understand, guys. For example, you have got an acid HA. Let's say you have got an acid HA. Since you know this acid, it will be losing H positive. When it loses H positive, this acid gets converted into A negative. Right? Acid after losing H positive, gets converted into A negative. Now understand one thing. Acid after losing H positive gets converted into A negative. Remember, if this is the acid, then this A negative is something which we call as the conjugate base. We call it as the conjugate base of this particular acid. An acid after losing H positive gets converted to something. That something I'll be calling as the conjugate base. And remember, my dear students, remember from now onwards, acidic strength of an acid is directly proportional to the stability of the conjugate base. Acidic strength of an acid is directly proportional to the stability of conjugate base. And if you have studied your equilibrium, well, I have already taught equilibrium on this channel, right? So remember, we have studied acidic strength is also directly proportional to Ka, inversely proportional to pKa. Right? What is Ka? What is pK? If you have not studied equilibrium, just remember it for now. Sometimes the questions will be directly asked based on acidic strength. Sometimes they'll give the question as per Ka, give the order of Ka. Sometimes they'll give the question as per pKa, right? Yeah? Perfect. Perfect, people. Now, the point is, acidic strength, it is directly proportional to the stability of conjugate base. More stable the conjugate base, stronger is going to be this acid. And stronger the acid, more will be the Ka value. Lesser will be the pKa value. Now try to understand how I'll be using this particular concept to solve the questions which are based on your acidic strength. Try to understand very carefully. Okay? Try to understand very carefully. See guys, I have to compare the acidic strength of these two acids. I have to compare the acidic strength of these two acids. What I will be doing? Acidic strength of an acid is directly proportional to the stability of conjugate base. So let's try to make the conjugate bases of these acids. How do you make the conjugate base? Do one thing, take H positive out. When you take H positive out, you get RO negative. Take H positive out, you get RS negative, right? Negative charge on oxygen, negative charge on sulfur. Well, if these are the acids, then these are the conjugate bases. So I made the conjugate bases of these acids. Now talk about the stability of these conjugate bases. My dear students, oxygen carrying negative, sulfur carrying negative, oxygen carrying negative, sulfur carrying negative. Oxygen and sulfur, they belong to same group. And in the group, VCD dominates. In the group, VCD dominates. More the size, lesser the VCD, more the stability. So this conjugate base is more stable. So its acid will be stronger. Because acidic strength is directly proportional to stability of conjugate base. Right? Understood, people? So whenever you have to give the order of the acidic strength, make the conjugate base and see the stability of the conjugate base. That acid that gives the stable conjugate base is going to be stronger acid. Yeah? Right? Right, people? Now talk about this one. Give the acidic strength here. So make their conjugate bases. So take H positive out from here. If you take H positive out, it becomes CH3 negative. Take H positive out from here, it becomes NH2 negative. Take H positive out from here, it becomes OH negative. Take H positive out from it becomes F negative. So these are the conjugate bases first of all. Carbon carrying negative, nitrogen carrying negative, oxygen carrying negative, fluorine carrying negative. Right? Well, all these elements which I've underlined, they belong to same period. And in the period, electronegativity dominates over VCD. Right? And you know, negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element. So this conjugate base will be maximum stable, and more the stability of the conjugate base, stronger is going to be its acid. So this is the acidic strength order. Yeah? Done. Perfect, guys. Talk about this one. H2O and H2S. Take H positive out. What do you get? You get OH negative. Take H positive out. What do you get? You get SH negative. SH negative. Oxygen carrying negative. Sulfur carrying negative. Oxygen carrying negative. Sulfur carrying negative. Now oxygen and sulfur, they belong to same group. And in the group, you talk in terms of VCD. So sulfur has got more size than oxygen. More the size, lesser the VCD. Lesser the VCD, more the stability. So this conjugate base is more stable. So its acid will be stronger. So H2S will be stronger acid than H2O. Yeah? Now, if you look at this particular case, again, my dear students, take H positive out, there'll be negative charge here. Take H positive out, there'll be negative charge here. Take H positive out, there'll be negative charge here. Now compare the stability of the conjugate bases. Triple bonded carbon, double bonded, single bonded. Triple bonded carbon means more S character. More S character means more electronegativity. And you know, negative charge is more stable and more electronegative. So the conjugate base that gets formed here, that is more stable. More stable the conjugate base, stronger is going to be the acid. Yeah? Right, people? Am I clear? Now, can you talk about the acidic strength of these two here? Can you compare their acidic strengths? Can you compare their acidic strengths? Well, you should be in a position to compare. See, when you take H positive out from here, this will be carbon carrying negative. When you take H positive out from here, it becomes NH2 negative. NH2 negative when you take H positive out. This nitrogen carrying negative, carbon carrying negative. Now understand, normally if you see, Carbon and nitrogen, they belong to the same period. In the period, electronegativity dominates. So negative charge is more stable or more electronegative. So technically I should say that the conjugate base that gets formed here should be more stable. But few minutes back I told you, this is your sp hybridized carbon. This is sp3 hybridized nitrogen. And electronegativity of sp hybridized carbon is more than that of sp3 hybridized nitrogen. So this carbon here will be more electronegative, and negative charge is more stable or more electronegative, and more the stability of the conjugate base, stronger is going to be the acid. So tell me once in the chats if you can solve all the types of the questions based on the concepts which I discussed till now. Yes, people? Everyone in the chats, quickly. Everyone in the chats, quickly. Is every single thing clear till here? Say yes or no in the chats, everyone. After that only I'll continue. Yeah? Believe all of this is clear to everyone, yeah? Okay, let's move on and talk about one important concept of this chapter. That is that's your inductive effect. Yeah? That's your inductive effect. What this inductive effect is all about, what kind of questions can be framed from inductive effect. Let's talk about that one by one. So first of all, let me try to write statement here. Let me try to write a statement here. What is the inductive effect? My dear students, note down the definition with me, whatever I'll be writing on the screen. Whenever an atom or group of atoms, whenever an atom or group of atoms is attached to the carbon chain, comma, the chain becomes partially polarized. The chain becomes partially polarized due to the transmission of sigma electrons. And let me tell you, this phenomenon is called as the inductive effect. This phenomenon is called as the inductive effect. So let's try to understand. What it means exactly. How do we understand all this? See, guys. For example, I'm taking a carbon chain here. Let's say this is the chain containing 5 carbon atoms. This is the carbon chain. Okay. This is the carbon chain. And this carbon is, for example, attached with hydrogen here, right? This carbon is attached to hydrogen. I'm not showing all the other hydrogen atoms. That's understood. I'm just showing a chain wherein carbon is linked to the single bond, and this carbon is finally attached with hydrogen. Okay. Now, my dear students, what I'll be doing exactly? I am going to replace this hydrogen. With this hydrogen. With what? I'm going to replace this hydrogen by some atom or some group of atoms. I'm going to replace this hydrogen by some atom with some atom or some group of atoms. So what do I get here? For example, this is your carbon chain. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Perfect. Now I have replaced hydrogen with an atom X, for example. I've replaced hydrogen with an atom X. Similarly, I'm going to take one more case wherein this is your carbon chain 1, 2, 3, 4, 5, and I'm replacing this hydrogen with some atom Y. With some atom Y. Okay? Clear? Now, my dear students, let's assume that electronegativity of X is more than that of electronegativity of carbon. Let's say electronegativity of X is more than that of electronegativity of carbon. If electronegativity of X is more than that of electronegativity of carbon, can I say this X will attract the sigma electrons towards itself? This X will attract the sigma electrons towards itself, due to which this X gets delta negative and this carbon gets delta positive. As this carbon gets delta positive, it's going to attract this electron pair towards itself. So this carbon also gets delta positive, right? As this carbon got delta positive, it's going to attract this electron pair towards itself, due to which this carbon also gets delta positive. This carbon also gets delta positive, right? So do you see, when I attached an atom or a group with a carbon chain, what happened? What happened? This chain got partially polarized. This chain got partially polarized. Due to what? This chain got partially polarized due to the transmission of sigma electrons. This chain got partially polarized due to the transmission of sigma electrons. This phenomenon which you see over here, when you attach an atom or a group with a carbon chain, due to which the chain gets partially polarized due to the transmission of sigma electrons, this effect is what you call as the inductive effect. This effect is what you call as inductive effect. So I would say this group is showing, this atom or group here, it is showing inductive effect. Now guys, understand one thing. Is this group withdrawing the sigma electron density from the chain? Yes, this group, this atom or group, it is withdrawing. It's pulling the electron density from the chain, right? And that group, which withdraws the electron density from the chain, you call that group as, first of all, as the electron withdrawing group, right? And over here, I'll say this atom or group is showing minus inductive effect. We say this atom or group, which is decreasing the electron density in the chain, which is pulling the sigma electron density from the chain, right? Which is withdrawing the sigma electron density from the chain. We say this group shows which kind of inductive effect? It shows minus inductive effect. Yeah. Now similarly, guys, look at this particular case. Let's assume that electronegativity of carbon is greater than that of Y. If electronegativity of carbon is greater than that of Y, what's going to happen? This carbon will attract the electron density towards itself. And when the carbon attracts electron density towards itself, this will get delta negative, this will get delta positive. Now this delta negative will repel this electron pair. When it repels this electron pair, this carbon also gets delta negative. And this delta negative will again repel this electron pair towards this particular carbon. This also gets delta negative, right? So I would say, when I attached an atom or group with the carbon chain, the chain got partially polarized due to the transmission of sigma electrons. Due to the transmission of sigma electrons, this phenomenon I'll be calling as the inductive effect. Now I would say this particular group, is it withdrawing electron density or donating? It is pushing the electron density in the chain. It is pushing the electron density. It is pushing the sigma electron density in the chain. Right? It is pushing the sigma electron density in the chain. And whenever you see such a group that pushes the sigma electron density in the chain, you call that particular group as the electron donating group. And my dear students, we say at this particular point of time, the group shows plus inductive effect. So whenever from now onwards, you see plus I means electron donating, minus I means electron withdrawing. Yeah? Am I clear, people? Am I clear? Everyone in the chats once. Am I clear, people? Everyone in the chats? Yeah? Someone has started to spam. Go to this organization. Why you are studying here? Because they don't have Wassim but there. Okay? That's why they are here. Am I clear, people? Quickly. Yeah? I hope all the things are clear till here. Okay, now let's try to understand a few more things, guys. Let's try to understand a few more things. I believe these two things are already clear to everyone. That group or atom which decreases the sigma electron density in the chain, we say that group shows minus I effect. That group or atom which increases the sigma electron density in the chain, we say that group of atom shows plus I effect. Yeah. Now the point is, this plus I and minus I, they are relative. They are relative. What does that mean? Plus I and minus I, they are relative terms. So when we say plus I, that is with respect to something which will be showing minus I. When we say minus I, that is with respect to something that will be showing plus I. What does that mean? Try to understand. Try to understand. If you talk about this carbon, this particular carbon, I would say the electronegativity of this carbon is more. Why? Because three-membered, more angle strain. And the electronegativity of this carbon is comparatively less. So if electronegativity of this carbon is more, it will attract the sigma electron density towards itself, due to which this gets delta negative, this gets delta positive. If you talk about this group, is this group withdrawing the electrons? Yes, it's electron withdrawing here. So technically I would say it is showing minus I. But if you talk about this particular group, can I say this group is pushing the electrons? It is pushing the electrons. So technically it is donating. It shows plus I. So plus I and minus I, they are related to each other. A group shows minus I with respect to something that shows plus I, and this shows plus I with respect to something that shows minus I. Right? Same goes for this one. Talk about this particular carbon. This is sp hybridized. Talk about this particular carbon. This is sp2 hybridized. S character of this carbon is more. S character of this carbon is more. If S character of this carbon is more, it will attract the sigma electron towards itself, due to which delta negative, delta positive. So if I talk about this particular group here, if I talk about this particular group, can I say this group is withdrawing the electrons? So it is technically showing minus I. But if you look at this particular group simultaneously, this particular group, it is pushing the electron density, right? So I would say it is showing what? It is showing plus I. It's showing plus I. So plus I and minus I, they are related to each other. They are related to each other. Yeah? They are related to each other. Now there are a few important parameters which you need to know, which you need to remember to solve the questions. And what are those parameters? What are those parameters? Try to understand. Remember, there are some minus I showing groups which you need to know. There are some minus I showing groups. And all your cationic groups, those groups which carry positive charge, all your cationic groups, those groups which carry positive charge, all your cationic groups, they are electron withdrawing. They show minus I power. They show minus I effect. And remember, minus I power of cationic group will be greater than that of minus I power of the neutral group. Minus I power of the cationic group, that will be greater than that of minus I power of the neutral group. Right? And all your halogens, fluorine, chlorine, bromine, iodine, they show minus effect, minus I effect, minus inductive effect. These are few points, my dear students, which you need to know, which you need to remember. Okay? First of all your cationic groups, their minus I power, all your cationic groups, they are going to show minus I. They are going to be withdrawing in nature. Minus I power of cationic group will be greater than that of minus I power of the neutral group. One more thing. And my dear students, all your halogens, they show minus I effect, right? If you talk about these groups, groups like OH, groups like NH2, NO2, CN, right? C double bond O, C double bond OH, COR, COOR, all these groups, they show minus inductive effect. How they show minus inductive effect? It's pretty much simple. For example, you're attaching this group with a carbon chain. You're attaching this group with a carbon chain, right? You're attaching this group with a carbon chain. Perfect. What's going to happen? Oxygen is more electronegative than carbon. So it will pull the sigma electron density towards itself, right? So it shows minus I. Let's say you're attaching this particular group with a carbon chain. This nitrogen, it is more electronegative than the carbon of the carbon chain. So it will withdraw the sigma electrons towards itself. Again minus I, again minus I, again even this is C triple bond N. This is C triple bond N, right? You're attaching this group with a carbon chain, for example. This is a carbon chain, for example. Perfect. Now this carbon is sp hybridized. Sp. This carbon will be, for example, sp3 hybridized. Electronegativity of this carbon is more. If electronegativity of this carbon is more, that means it will pull the sigma electron density towards itself. So this particular group again shows which effect? Minus I effect. Yeah. Similarly, my dear students, this is, for example, a group which is attached with a carbon chain. Now what's going to happen? This is carbon double bond O. So oxygen gets delta negative, carbon gets delta positive because oxygen is more electronegative. Now this carbon getting delta positive, it is going to pull the sigma electrons towards itself. So this particular group, it's withdrawing the electron density, right? So again minus I. This also shows minus I because of this delta positive, delta negative here. This also shows minus I because of this delta positive, delta negative. This also shows minus I because of delta positive, delta negative, right? So all these groups are basically your minus I showing groups. Perfect. So what all things we have to remember? All are cationic groups. They show minus I effect. They're withdrawing in nature. Number two, my dear students, if I talk about your minus I power of cationic groups, remember minus I power of cationic groups is more than that of minus I power of the neutral groups, right? Your halogens, they will be showing minus I. And all these groups which are mentioned over here, right, they are your minus I showing groups. Okay, minus I showing groups. Similarly, if I talk about plus I showing groups, all your anionic groups which carry negative charge, all your anionic groups, when you attach them with a carbon chain, they are going to show plus I effect. They are going to be electron donating in nature. They are going to be electron donating in nature. Number one. Number two, plus I power of anionic group will be greater than that of neutral group. Plus I power of anionic group will be greater than that of plus I power of neutral group. Point number two. Point number three, all alkyl groups. For example, this is your methyl. This is C2H5, your ethyl, right? All your alkyl groups, they are going to show what? They are going to show plus I effect. Why is that? Why they are going to show plus I effect? Why this alkyl group will show plus I effect? See, if you talk about carbon and hydrogen, which one is more electronegative? Carbon. So it will attract this electron density towards itself, due to which this carbon gets delta negative. From all the sides, it's getting delta negative. So this delta negative and this electron pair, right? Between carbon and this carbon of the chain, right? There is electron pair. Now this delta negative will repel this electron pair. It will repel this electron pair, due to which this is the direction. This is the direction of transmission of sigma electrons. So I would say this particular group, is it withdrawing the electron density or pushing the electron density? It is pushing the electron density towards the chain, right? So I would say this group is going to show plus I effect. This is showing plus I effect. Right, people? Am I clear? Am I clear? Everyone in the chats? Am I clear? Everyone in the chats? Whatever things I've discussed till now, are all these things like very, very, very clear to you? Okay. Now, guys, one more important thing. Remember, plus I power of the group. That is directly proportional to the number of branches at the free valent carbon. What does that mean? This is again an important statement which will be used in the questions. See, first of all, this is a group which we have. If you look at this particular group, let's say this group is attached with a carbon chain. Now, this particular carbon of the group which is attached with the carbon chain, I call this particular carbon as the free valent carbon. I call this particular carbon as the free valent carbon. Free valent carbon. So how many branches this free valent carbon has? This free valent carbon has got one branch and this second branch. So this free valent carbon, it has got two branches. It has got two branches. Similarly, talk about this one. Let's say this particular group is attached with a carbon chain, right? And this is the carbon of the group which is attached with the chain. So I'll be calling this particular carbon as the free valent carbon, right? So how many branches do you see? 1, 2, 3. 3 branches. Here, the free valent carbon has got 3 branches. Remember, minus I power of that particular group. Sorry, I'm not talking about minus I, I'm talking about plus I right now. Because all the alkyl groups, they show plus I, right? So plus I power of that particular group, where the free valent carbon has got more branches, is always going to be more. Okay? So plus I power of this particular group will be more. Why? Because at the free valent carbon, you have got more branches here. You have got more branches here. Am I clear? Am I clear with this? Yeah? Similarly, guys, what if the number of branches at free valent carbon are same? What do we do at that time? What if the number of branches at the free valent carbon are same? What do we do at that time? See, this is the free valent carbon which will be attached with the carbon chain. Here, this is the free valent carbon which will be attached with the carbon chain. Here, this is the free valent carbon which will be attached with the carbon chain, right? Now, this free valent carbon, it has got only what? I would say it has got only one branch. This is the branch. This free valent carbon, it has got only one branch. This free valent carbon, it has got only one branch. So, the branches are same here. So, talk in terms of the number of carbon atoms in the branch. The number of carbon atoms, here, 1. Here you have got 2. Here you have got 3. Right? So, more the number of carbon atoms in the branch, more is going to be the plus I power of the alkyl group. Right? But this is valid only if the free valent carbon has got same branches. Perfect? So, I would say simply, plus I power of this group will be more than that of this group, will be more than that of this group. And similarly, talk about your hydrogen. Hydrogen has got 3 isotopes. Protium, deuterium, tritium. Right? Protium, deuterium, tritium. Tritium will be having more plus I, followed by your deuterium, followed by your protium. Okay? And there is one more thing, guys. All these points I'll be using in the questions in some time. Like in 5 to 10 minutes. I'll be doing all the questions which are based on inductive effect. But to do the questions, you have to remember all of this over here in detail. Yeah? One more thing, guys, which I will tell you here. What is that? This inductive effect. This inductive effect. We consider the inductive effect only up to 3 carbon atoms. We consider inductive effect. We take inductive effect. We consider inductive effect only up to 3 carbon atoms. For example, if you see here, I only showed the charges till 3 carbon atoms. I only showed charges till 3 carbon atoms because we believe that inductive effect, it diminishes, it vanishes after 3 carbon atoms. Because you know, inductive effect, it is distance dependent, right? Which will vanish after 3 carbon atoms. So you're going to take inductive effect till 3 carbon atoms only. Okay? Now, arrange the following according to minus I power. Can you arrange them as per minus I power? See, this is your atom. I mean, fluorine, you have got chlorine, you have got bromine, iodine. Let's say you're attaching them with the carbon chain. Let's say you're attaching them with the carbon chain. Perfect. These are all halogens. And halogens, as I told you a few minutes back, they show minus I. Now, which halogen will show more minus I? See, which halogen will show more minus I? Quickly. This is something which you should know, guys. Chlorine is more electronegative. More electronegative means it will withdraw the sigma electron density from the chain more towards itself. So, this is going to be the minus I power here. Chlorine attached with the carbon chain, oxygen attached with the carbon chain, nitrogen attached with the carbon chain. Which one is more electronegative? Fluorine, right? So, it will withdraw the sigma electrons maximum towards itself. So, this is the minus I power, right? Cationic groups. The minus I power of cationic group is always greater than that of minus I power of neutral group. A few minutes back only I told you, right? Perfect. Now, oxygen attached with the carbon chain, nitrogen attached with the carbon chain. Oxygen is more electronegative, so it will withdraw sigma electron density more towards itself. So, more minus I. Yeah. Look at this one. triple bonded, double bonded, single bonded. So this carbon has got more S character as compared to this particular carbon, as compared to this particular carbon. So more the S character, more the electronegativity, more will be its tendency to withdraw the sigma electrons from the chain. So this is the minus I power, right? This is the minus I power. I believe I'm clear. Now, can you tell me among these three groups, which one has got more minus I here? Can you tell me among these three groups, which one has got more minus I here? Quick, 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 everyone. Which one will be having more minus I? See guys, first of all, this is the group and this carbon will be attached with the carbon chain. This carbon will be attached with the carbon chain. Here, this carbon will be attached to the carbon chain. This is carbon oxygen, right? Polar. Oxygen is more electronegative, so delta negative, delta positive. Again, delta positive. This nitrogen, delta negative. Perfect. Right? Now, this is carbon, so nothing will happen. Now, tell me one thing. Oxygen is more electronegative. If oxygen is more electronegative than nitrogen, oxygen is more electronegative than nitrogen, so oxygen has got more tendency to pull these electron pairs towards itself, due to which the magnitude of positive charge here, will be more than the magnitude of positive charge on this carbon. Right? Answer is pretty much simple. Carbon here is attached with oxygen. Here it is attached with nitrogen. Right? Oxygen is more electronegative. It will pull the shared pair of electrons towards itself more than that of nitrogen, due to which this carbon gets more delta positive. Right? More the delta positive, right? More will be its tendency to withdraw the sigma electron density from the chain. Right? So this is the minus I power. This is the minus I power. Now this is cationic, this is cationic. Which one will have more minus I power? Now nitrogen attached with 3 fluorine atoms, 3 electronegative. Fluorine is electronegative, right? So 3 electronegative atoms attached. Here nitrogen is attached with 3 hydrogens, right? So these 3 fluorines which we have, this is your N, this is F, and this is F, right? And NF3 positive, and then you have got NH3 positive. Since fluorine is more electronegative than that of hydrogen, of course, right? So it will increase the magnitude of positive charge on nitrogen here. If it increases the magnitude of positive charge on nitrogen, this nitrogen becomes more withdrawing, right? So this is the order. This is the order. Now, give me the minus I power of these groups. Nitrogen carrying positive, phosphorus carrying positive, arsenic carrying positive, antimony carrying positive. See, nitrogen, phosphorus, antimony, and arsenic, they belong to the same group. And in the group, we talk in terms of VCD. We talk in terms of volume charge density, right? We talk in terms of volume charge density. Now you tell me, what is going to be the answer? Volume charge density and size, they are inversely proportional. Lesser the size, more the volume charge density. So this nitrogen here, it has got more positive volume charge density than that of this one, And more the positive volume charge density, more is the withdrawing nature. So it will show more minus I. Same is the reason here. Now NR3 positive and NH3 positive. Normally, what do you think? Normally, you'll think that NH3 positive should have more minus I power than that of NR3 positive. But it is a reverse here. Why is that? See, if you talk about NR3 positive, so basically, if you normally think this R, it will push electrons towards nitrogen. This will also push electrons towards nitrogen. This will also push electrons towards nitrogen, due to which the magnitude of positive charge should be decreased. It should be technically decreased, right? So I would say positive charge on this nitrogen should be more than that of this. So technically, this should be more withdrawing, but this is not more withdrawing. Why is that? Because you have got R groups, bulky groups attached here, due to which there will be repulsions. More repulsions means more bond angle. More bond angle means more S character. More S character means more electronegativity. So that is the reason why your NR3 positive is more withdrawing. Yeah? Right? I believe I'm clear till here. And my dear students, I'll be giving you 2 series, minus I series and plus I series. You have to remember it, right? NF3 positive has got maximum minus I, followed by NR3 positive, followed by NH3 positive, NO2, CN. You can make any mnemonic to remember this particular series. This is the minus I power series. Similarly, this is the plus I power series. Whatever mnemonic you want to make, you can create a mnemonic on your own based on your convenience, right? So, because this series you have to remember, guys. This series is important, you have to remember it. This series is important, you have to remember it. Now comes a point with the help of which we are going to solve the questions. Where do we use this inductive effect? Where do we use this inductive effect? My dear students, the first application, the first application of inductive effect. What is the first application of inductive effect? That is the stability of a carbocation. Stability of carbocation. Let me tell you, my dear students, carbocation is stabilized by electron donating groups. Carbocation is stabilized by electron donating groups. Electron donating groups. See, if this is the carbocation, right, and there is electron donating group attached, electron donating group will push some electrons towards carbon, due to which the intensity of positive charge will decrease, and lesser the charge on the atom, you'll say more will the stability, right? Lesser the charge, more the stability, correct? Lesser the charge, lesser the potential energy, that means more the stability. So remember one simple thing. Stability of carbocation is, a carbocation is stabilized by electron donating group, and a carbocation is destabilized by electron withdrawing group. So if I talk in terms of inductive effect, carbocation is stabilized by plus I showing group, and carbocation is destabilized by minus I showing group. This is the first sort of the question that will be asked. Number two, let me talk about the stability of Carbanion. Carbanion, carbon carrying negative. Carbanion, it is stabilized by electron withdrawing group, and it is destabilized by electron donating group. Why is that? Let's say this is carbon carrying negative. This is the Carbanion, for example. Now you have got an electron withdrawing group attached with it. This electron withdrawing group, it will pull the sigma electrons towards itself, right? Due to which the magnitude of negative charge here will try to decrease. If the intensity of negative charge decreases here, I would say the potential energy decreases, stability increases. So electron withdrawing group. If I talk about electron withdrawing group, it stabilizes the Carbanion, and electron donating group, it destabilizes the Carbanion. And at the same time, people, remember, if I talk in terms of inductive effect, electron withdrawing means minus I. Electron donating means plus I. Okay. This is the second question that will be asked here. My dear students, third question. Third question will be acidic strength. And you know, acidic strength is directly proportional to what? It is directly proportional to stability of conjugate base. And remember, a conjugate base wherein you will have a negative charge. A conjugate base is stabilized by electron withdrawing group and destabilized by electron donating group. Electron withdrawing means minus I, electron donating means plus I. Okay. And similarly, people, if this is the order for acidic strength, then similarly, if I talk about the basic strength, basic strength, just reverse of acidic. So electron donating group increase the basic strength, and electron withdrawing group decreases the basic strength. So electron donating means plus I, electron withdrawing means minus I. So this is something which you have to remember. And if you remember this table, I am telling you, you will be in a position to solve each and every question. Right? Okay? Am I clear, people? I'm not going to give you the dinner break, guys. It will take me not more than 20 minutes to complete this session. I told you I'll be completing GOC in 3 sessions maximum, right? Okay, and every session duration will be 2 to 3 hours, between 2 to 3 hours. So basically, there are total 6 topics which are to be covered in this particular chapter. So these are the six topics, out of which I have marked here these two. These two will be discussing in the today's session. So now let's see what kind of questions can be asked from inductive. And let me tell you, these two I'll be doing on Wednesday, right? And these two will be done on Saturday. Same timing. Okay? Now guys, let's try to solve some questions which will make things easier for you. Which will make things easier for you. Which will make things easier for you. We have to arrange the following carbocations on the basis of the stability order. Well, carbocations, basically, when you talk about the stability of carbocations, the first thing that should come into your mind, that is hyperconjugation, right? Which you would have studied many a times. Till now, we have not discussed hyperconjugation. So I'm not going to answer any question based on hyperconjugation. I'll be answering all these questions based on inductive effect. Whatever questions we have, I'll be answering all the questions based on inductive effect because we have only discussed inductive effect till now. We have not discussed any hyperconjugation or something like that. Okay, have a look. This is carbon carrying positive, this carbon carrying positive, single bonded carbon, double bonded carbon. This has got more S character. More S character means more electronegative. And positive charge is more stable on less electronegative. So this is the order. Carbon carrying positive, carbon carrying positive, carbon carrying positive. So how many electron donating groups? Alkyl groups, electron donating, electron donating, electron donating. More the electron donating groups, more the stability of carbocation. So this is the stability order. Simple. Right? Correct? Talk about these questions. This is your carbon carrying positive, carbon carrying positive, carbon carrying positive. Now CH3 plus I showing group, right? CD3 again plus I showing group. NO2 nitro minus I showing group, right? This is donating, this is donating, this is withdrawing, right? Carbocations are stabilized by electron donating groups, right? This is donating, this is donating. Now which one shows more plus I? CD3. The series which I gave you, in that series it's mentioned, CD3 is more electron donating, right? So B will be maximum stable, followed by A, followed by C. Because C here, it's withdrawing and electron withdrawing group, they destabilized the carbocation. Okay? Now talk about this one. Carbon carrying positive, carbon positive, carbon positive. Here you have got nitro, minus I showing. Here you have got nitro, minus I showing. Inductive effect is distance dependent, right? Here, this electron withdrawing group is closer, right? So its minus I power will be prominent here. It is closer, right? Its minus I power will be prominent here. Perfect. Or I would say it will intensify this positive charge here more than that of this particular case, right? So tell me, what is going to be the stability order? Quick. Which carbocation is going to be more stable? See, electron withdrawing groups, they destabilize the carbocation, right? So first one is going to be maximum stable, then comes your second one, then comes your third one. Okay, then comes your third one, because electron withdrawing groups, they destabilize the carbocation. All right, carbon positive, carbon positive, carbon positive. Here you have got CD3, it shows plus I. CD3, it shows plus I. CD3 shows plus I. So all are electron donating groups. All are electron donating groups. Electron donating groups, they stabilize the carbocation. Electron donating groups, they stabilize the carbocation. Right? Okay. Now, electron donating groups, they stabilize the carbocation. Now, plus inductive effect. Inductive effect is distance dependent. So plus I will be prominent here. Right? So it will stabilize the carbocation, the maximum. So this is the stability order. So it will stabilize the carbocation here, the maximum, right? Now, if you talk about this one, look at this particular group, alkyl group. Here also you have got alkyl group. Here you have got alkyl group, right? Now, alkyl groups, they show plus I. So they are donating. They are electron donating. So they are going to increase the stability of carbocation. Now, look at this free valent carbon. It has got one branch. Look at this free valent carbon. It has got three branches. Look at this free valent carbon. It has got two branches. More the branches, more plus I. More the branches, more plus I. More plus I means more donating. More donating means more stability of the carbocation. So B will be more stable, followed by C, followed by A. Right? Give me the order of the Stability of the carbocations here. See guys, first of all, this is your alkyl group. It is going to show plus I. Nitro group is going to show minus I, right? CN is going to show minus I. This is withdrawing, but this is donating. Donating group, they stabilize the carbocation, so A is maximum stable. Now, B is more withdrawing. If NO2 is more withdrawing, that means it will destabilize the carbocation to the maximum. So B, I'll prioritize the least. C comes in the middle. ACB is the order. Right? Look at this one. This is the carbon carrying positive. This is the carbon carrying positive. Here you have got double bond, sp2, sp2. Here, everything is sp3. So here you have got more S character. More S character means more electronegative. And more electronegative means more withdrawing. More withdrawing means carbocations are destabilized by withdrawing groups. So this is the stability order. Right? Now, again we are given with carbocations. CD3, this is plus I showing. CH3, again plus I. T3, again plus I. Right? So all are donating groups. And electron donating groups, they stabilize the carbocation. Now, which group shows more plus I? CT3 shows more plus I. In the series, it's mentioned CT3. It shows more plus I. So if it shows more plus I, so it's going to stabilize the carbocation to the maximum. So C is maximum stable, followed by A, followed by B. So CAB is the order. Okay. See guys, carbon carrying positive, carbon carrying positive, carbon carrying positive. Nitro, withdrawing. Chlorine, withdrawing. Which one is more withdrawing? This nitro. An electron withdrawing group, they destabilize the carbocation. So B is the least stable, right? Then comes your C, right? The most stable is going to be A, because you have got this particular group attached, which is alkyl group. Alkyl group show plus I, right? I believe I'm clear. This particular question we have already solved. More the alkyl groups attached, more the stability. More the electron donating groups, more the stability of the carbocation. Now, talk about this particular one, this particular one, this particular one, right? See, if you talk about this carbon having positive, it is getting electron density from one side. This carbon is getting electron density from all the three sides. This carbon is getting electron density from two sides. So which one is going to be more stable? So B will be more stable, followed by C, followed by A, right? This is CH3, this is CH2D, CHD2, CD3. Deuterium is more donating. It shows more plus I. It is more donating than that of protium. 2 minutes back we have seen. You have got 3 deuteriums here, 2, 1, right? So this is the stability order. Is it clear, guys? Whatever I'm telling you? Deuterium is more donating. Deuterium is more donating than that of protium. Perfect. So here you have got 3 deuteriums. Perfect. More the donating groups, more the stability of the carbocation. If you talk about this one, nitro minus I, CN minus I, fluorine minus I. Right? And I would say all these are electron withdrawing. If they are withdrawing, they are going to destabilize the carbocation. They are going to destabilize the carbocation. This is maximum withdrawing. So the stability of this carbocation will be least. So A will be least stable. A will be least stable. Right? Can you tell me among these two? Among these two quickly. B or C, which one is maximum stable? Which one is maximum stable? Since these are carbocations, guys. Since these are carbocations, quickly. In the chats. Or you can give me its order in the chats, in the comment section. Once we end this particular session, tell me the answer of this particular question in the comment section of this particular video. Once the video ends, so leave it as such. Talk about this one. Arrange the following carbanions as per the stability. Arrange the following carbanions as per the stability. See, sulfur carrying negative, oxygen carrying negative. Sulfur and oxygen, they belong to same. Sulfur and oxygen, they belong to same group. They belong to same group. In the group, VCD plays a role. Sulfur has got more size. More the size, lesser the VCD. Lesser the VCD, more the stability. So negative charge is more stable here. Correct? If you remember, this was your sp hybridized carbon. And this was your sp3 hybridized nitrogen. Perfect? The electronegativity of sp hybridized carbon is more. and negative charge is more stable and more electronegative. Why I used electronegativity rule here? Because carbon and nitrogen, they belong to same period. They belong to same period. I hope this is also clear. I'll be providing the PDF of this session. Yes, I'll be providing the PDF of this session in the Telegram. Wassim but Chemistry Official. That is a Telegram channel. These are all Carbanions. Carbon carrying negative, carbon carrying negative, carbon carrying negative. Now, this is electron donating, plus I. This is electron withdrawing, minus I. This is also electron withdrawing, minus I. And carbanions are stabilized by electron withdrawing groups. Carbanions are stabilized by electron withdrawing. Now, which one is more withdrawing? Nitro is more withdrawing. So, it will stabilize the carbanion the maximum. Followed by what? Followed by B. Followed by E. This is the stability order. Okay. NF3 positive. Withdrawing. Fluorine. Withdrawing. CD3. Donating. All these are carbanions. Negative charge everywhere. And carbanions are stabilized by electron withdrawing. Carbanions are stabilized by electron withdrawing groups. So this is withdrawing, this is withdrawing. Which one is more withdrawing? This is more withdrawing. Carbanions are stabilized by electron withdrawing groups. This is more withdrawing. So it will stabilize the carbanion the maximum. So A will be maximum stable, followed by B, followed by C. Okay. Perfect, guys. Tell me the order of this particular question. Tell me the order of this question. Again, there's a negative charge here, negative charge here, negative charge here. Correct? And your carbanions are stabilized by electron withdrawing. Electron withdrawing. Here you have got oxygen. Here you have got oxygen comparatively closer. There is no oxygen here, right? Oxygen is withdrawing. If oxygen is withdrawing, right? So I would say B will be maximum stable, followed by A, followed by C. Because electron withdrawing groups, they stabilize the carbanion. Talk about this one. Sulfur carrying negative, oxygen carrying negative. First of all, compare these two. Sulfur and oxygen, they belong to same group. In the group, VCD plays a role. Sulfur has got more size, more the size, lesser the VCD. Lesser the VCD, more the stability. So A is more stable than that of B. Now, among oxygen and nitrogen, they belong to same period. In the period, it's going to be electronegativity that dominates. Oxygen is more electronegative and negative charge is more stable and more electronegative. So B will be more stable than C. Similarly, C will be more stable than D. ABCD is the order. Did you understand? Among nitrogen and carbon, they belong to same period. In the period, electronegativity plays a role, right? Nitrogen is more electronegative than carbon. Negative charge is more stable and more electronegative. So I would say negative charge is more stable here than that of this. So C is more stable than D. Correct? Okay. Again, negative. Fluorine, electron withdrawing. But fluorine is more withdrawing than that of iodine, right? So electron withdrawing groups, they stabilize the carbanion. So this fluorine is more withdrawing. So it will stabilize this carbanion the maximum. So the stability of this one will be more than that of B. F negative, I negative. Where is the negative charge more stable? Fluorine and iodine, they belong to same group. And in the group, VCD plays the role. More the size, lesser the VCD. Lesser the VCD, more the stability. Done. Understood. Arrange the following according to their acidic strength. Quickly, guys. Arrange the following as per the acidic strength. First of all these are your carboxylic acids. C double bond OH, C double bond OH, C double bond OH. Right? Here you have got a withdrawing group. Here you have got hydrogen attached. Here you have got donating group, right? And I told you already, acidic strength is directly proportional to the stability of the conjugate base, and the stability of conjugate base is stabilized by electron withdrawing groups. Few minutes back only we discussed. Conjugate base is stabilized by electron withdrawing. So here the conjugate base will be maximum stabilized. So acidic strength of A will be maximum, followed by B, followed by C. Okay. Now among these four, if you look, this is your carboxylic acid. If you look, this is your carboxylic acid. This is your phenol basically. Even this is your phenol. Correct? And remember, before going into the effects, before saying which group shows which effect, before talking about that, remember, acidic strength of carboxylic acids is more than that of acidic strength of phenols. Acidic strength of carboxylic acids is more than that of acidic strength of phenols. So definitely A and B will be more acidic than that of C and D. A and B will be more acidic than that of C and D. Because this is phenol, this is phenol. Phenols are comparatively less acidic than that of carboxylic acids. So A and B will be, first of all, more acidic than that of phenols. Perfect? Now I'm going to talk about the effect. Here nitro, minus I. Here CH3, plus I. Okay? And electron withdrawing groups, they increase acidic strength. So A will be more acidic than B. Now among C and D, minus I. Right? So C will be more acidic than that of D. This is the order, A, B, C, D. I hope I'm clear with this. All right. I believe all these questions you can do on your own. All these three are carboxylic acids, right? So arrange them on the basis of acidic strength. Now this is carboxylic, this is phenol, this is carboxylic. So this will be least acidic. So B will be least. Now among A and C you have to check. Among A and C you have to check. Among A and C you have to check. Here you have got withdrawing. Withdrawing groups, they increase acidic strength. So A will be maximum, followed, sorry, not A. C will be maximum, followed by A, followed by B. Correct? C will be maximum acidic here, followed by A, because this is also carboxylic, followed by B, because the B is phenol. Phenols are less acidic than your carboxylic acids. Give the order of acidic strength here. Again, you have got carboxylic acids. This is fluorine, withdrawing, 2 withdrawing, 3 withdrawing groups. More the withdrawing groups, more the acidic strength. Yeah? More the withdrawing groups means more the acidic strength. Why? Because more the withdrawing groups means more is going to be the stability of conjugate base. And more the stability of conjugate base, stronger the acid. Now look at this one. Phenol, this is carboxylic acid. Carboxylic acid is any time going to be stronger acid than that of phenols. So C is maximum acidic. Now among A and B, this is NF3 positive. It shows minus I. This also shows minus I. Now which one shows minus I among these two? Which one shows more minus I? NF3 positive shows more minus I. So more withdrawing means more stable will be the conjugate base. More stable the conjugate base means more the acidic strength. So A greater than B. Correct? Talk about this one. OH. Now at this particular carbon number 3, I've got fluorine. At carbon number 2, we have got fluorine. Fluorine is withdrawing. And electron withdrawing groups, they increase acidic strength, right? And you know, inductive effect is distance dependent. So inductive effect will be prominent here, where the withdrawing group is attached at second carbon. So more acidic will be first one. First one will be more acidic. Now among these 4, which one will be more acidic? So when you take hydrogen out as H positive, you will get negative charge here. You will get negative charge here, negative charge here, negative charge here. When you take hydrogen out as H positive. Then talk about the stability of conjugate bases. See, more angle strain means more electronegative. More withdrawing. More withdrawing means more acidic strength. More withdrawing means more acidic strength. Few minutes back we have discussed. More withdrawing means more acidic strength. Now these are two special cases. Compare their acidic strength. So when you take H positive out, what do you get? You get CF3 negative. When you take H positive out, what do we get? We get CCl3 negative, right? Now, these are the conjugate bases basically. Give me the stability order of these conjugate bases. Normally, what should we think? We should think that this conjugate base is more stable. Why? Because there are 3 fluorine atoms attached, right? 3 fluorine. More withdrawing. More withdrawing means more the stability of conjugate base. More stability of conjugate base means stronger has to be the acid. So this should be the order. But this is not the order. Order is like this. Why is that? Because if you talk about chlorine, in chlorine there are vacant d orbitals. In chlorine, there are vacant d orbitals. And if there are vacant d orbitals in chlorine, I would say there will be the chance of back bonding. There will be the chance of back bonding. And back bonding stabilizes the carbanion. Back bonding stabilizes the carbanion. More stable the carbanion, stronger is going to be its acid. Right? Stronger is going to be its acid. Now, if you compare these two, when you take hydrogen out as H positive, you'll get negative charge here. When you take hydrogen out as H positive, you'll get negative charge here. Right? Perfect. Now, sulfur, it has got a vacant d orbital. So there's a possibility of what? There's a possibility of back bonding here. And back bonding stabilizes the carbanion. Right? Back bonding stabilizes the carbanion. So what I'm trying to say is back bonding stabilizes the conjugate base. More stable the conjugate base, stronger is going to be the acid. So this is the acidic strength order. This is the acidic strength order. Right? I believe this is also clear. And my dear students, if this is clear, then can you give me the order of the basic strength? I've already given the rule. Basic strength is directly proportional to electron donating. Directly proportional to electron donating. Inversely proportional to electron withdrawing. Right? So basic strength is directly proportional to plus I. Inversely proportional to minus I. Now see, if you look at this particular nitrogen, see, it is forming 3 bonds, 3 sigma bonds and 1 lone pair. 3 sigma bonds, 1 lone pair. So 3 plus 1, 4. That means this sp3 hybridized. This nitrogen is sp2 hybridized. Right? Where is the S character more? Where is the S character more? S character is more here. More S character means what will happen? So this nitrogen will be holding its lone pair firmly. This nitrogen will be holding its lone pair firmly. So which one can donate the lone pair easily? This can donate the lone pair easily. And that particular species which can donate the lone pair easily, that particular species wherein lone pair can be donated easily, that is more basic. Right? Now talk about this one. This is nitrogen having lone pair, nitrogen having lone pair. So fluorine, chlorine. So first one should be more basic than that of second one because this one is more withdrawing. Right? Few minutes back only I've told you basic strength is directly proportional to what? Electron donating groups, inversely proportional to electron withdrawing groups. Or you can say directly proportional to plus I, inversely proportional to minus I. Okay? Right? Now guys, triple bonded nitrogen, double bonded, single bonded. Right? S character will be maximum here and S character will be least here. S character is least here means this will be less electronegative. If this is less electronegative, that means it can donate the lone pair easily. And that particular base which donates lone pair easily, that's going to be stronger base. So this is the basic strength order, 3 to 1. Am I clear with this, people? So our first lecture of GOC is done. As I told you already, the second lecture of GOC I will be doing on Wednesday, wherein I'll be discussing resonance effect, I'll be discussing mesomeric effect, and the third session is going to be on Saturday, wherein I'll be doing aromaticity and hyperconjugation. Right? I hope whatever things I've told you till now, I hope every single thing is like very, very much clear to you. Let me save this PDF for you so that I can share this on my Telegram. Okay. Okay, guys. So GOC part 2 I'll be doing on Wednesday and part 3 I'll be doing on Saturday. I hope whatever things I've discussed till now. Okay. I hope whatever things I've discussed till now, all the things are like very, very, very clear to you. Okay. Chalo guys. I'll be taking a leave with this. You also have your dinner. I'll see you in the next session, which is going to be on Wednesday. Okay. This session is already public on the channel. You can check it out. This session is already live on the channel. Go and click on notify me right now on that particular session. And do smash the like button too.